Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow. Let your body settle into wherever you are right now. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the day is finally winding down? Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most profound mysteries in modern cosmology. The universe is expanding faster than it should be, breaking rules we thought were fundamental to reality itself. We'll discover how scientists first noticed this impossible acceleration, understand what dark energy might be, and contemplate what it means that the cosmos refuses to behave according to our most elegant equations. It's a journey that spans the entire observable universe and reaches back to the first fraction of a second after the Big Bang. But don't worry, this isn't going to be an alarming race through cosmic catastrophe or a breathless countdown to universal doom. Instead, we'll move slowly and carefully through the observations, the theories, and the beautiful uncertainties that define this mystery. By the end, I think you'll find a strange comfort in the fact that the universe still has the capacity to surprise us, that there are still profound questions without answers. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this journey through the stars. So settle in, let your shoulders drop, take a slow breath, and let it out slowly. And let's begin our slow drift through the expanding universe. There's nowhere you need to be right now. Nothing you need to do. Just listen and let the story of our accelerating cosmos unfold around you, gently, like starlight reaching Earth after travelling for billions of years. For most of human history, we believed the universe was eternal and unchanging. The stars wheeled overhead in their predictable patterns. Constellations our ancestors named thousands of years ago still look the same today. This sense of cosmic permanence seemed obvious. Natural, right? Even when Copernicus displaced Earth from the centre of creation, even when Galileo turned his telescope skyward and multiplied the known stars by thousands, the fundamental assumption remained. The universe was static, stable, forever. Albert Einstein shared this assumption so deeply that when his own equations of general relativity suggested otherwise, when the mathematics indicated the universe must be either expanding or contracting, he added a term to force stability back into his theory. He called it the cosmological constant, and he later called it his greatest blunder. But perhaps we shouldn't judge him too harshly. Einstein was simply following centuries of intuition about how the cosmos should behave. The first crack in the steady universe appeared in 1929, when Edwin Hubble made observations at the Mount Wilson Observatory that changed everything. Using the most powerful telescope available at the time, Hubble measured the distances to distant galaxies and discovered something extraordinary. They were moving away from us. Not just a few of them, but all of them. And the farther away they were, the faster they were receding. This relationship between distance and velocity became known as Hubble's law, and it suggested something almost unimaginable. The universe was expanding, not into anything, but the space itself was stretching, carrying galaxies apart like dots on an inflating balloon. If you ran the expansion backward, like a film in reverse, all the matter and energy in the cosmos would converge to a single point, a moment of creation. The Big Bang. For decades after Hubble's discovery, cosmologists refined their understanding of this expansion. The universe began in an incredibly hot, dense state roughly 13.8 billion years ago. It expanded and cooled. Matter condensed from pure energy. Hydrogen and helium formed. The first stars ignited. Galaxies assembled themselves from the primordial chaos. And all the while, the expansion continued, slowing down gradually due to the mutual gravitational attraction of all the matter in the universe. This slowdown made perfect sense. Imagine throwing a ball into the air. Gravity pulls it back, slowing its upward motion until it stops and falls back down. Similarly, cosmologists expected gravity to slow the universe's expansion, perhaps even eventually reversing it in the underscore, quote, underscore, zero, underscore, underscore. The key question was whether there was enough matter in the universe to halt the expansion, or whether it would continue forever, gradually slowing but never quite stopping. Both scenarios seemed reasonable. Both followed naturally from the physics we understood. And this brings us to something equally remarkable. The moment when careful measurements revealed that the universe wasn't following either expected scenario, that something was fundamentally wrong with our understanding of cosmic evolution. In the 1990s, two independent teams of astronomers set out to measure the universe's expansion with unprecedented precision. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, both had the same goal: determine exactly how much the expansion was slowing down. They expected to measure the deceleration parameter, settle the question of the universe's ultimate fate, and refine our cosmic timeline. What they discovered instead earned them the Nobel Prize and opened a mystery that remains unsolved to this day. Their method was elegant and relied on a special type of stellar explosion called a Type I supernova. These occur when a white dwarf star accumulates matter from a companion star until it reaches a critical mass, about 1.4 times the mass of our Sun. At this threshold, the white dwarf undergoes catastrophic thermonuclear explosion, briefly outshining entire galaxies. The crucial feature is that these explosions are remarkably consistent. Because they always occur at the same mass threshold, they always produce roughly the same peak brightness. This consistency makes Type I supernovae what astronomers call standard candles. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate its distance. It's the same principle that lets you estimate how far away a streetlight is based on how dim it looks. But Type I, a supernovae, are streetlights we can see across billions of light-years of space, cosmic mile markers stretching back through time. The team searched for these supernovae in distant galaxies, measuring both their apparent brightness and their redshift. Redshift tells us how fast a galaxy is moving away from us. As space expands, it stretches the wavelength of light, shifting it toward the red end of the spectrum. Greater redshift means greater distance and faster recession. By comparing distance measurements from supernova brightness with velocity measurements from redshift, the teams could chart exactly how the expansion rate had changed over billions of years. Both teams analysed dozens of distant supernovae, checking and rechecking their data. The observations were technically challenging, requiring the world's most powerful telescopes and careful correction for numerous sources of error. Dust between galaxies could dim the light. The supernovae themselves might not be perfectly identical. Gravitational lensing by intervening matter could affect measurements. Every possible complication was considered, accounted for, eliminated. And when the results finally emerged in 1998, both teams found the same impossible thing. The distant supernovae were dimmer than they should be. Not by a little, but by a consistent, measurable amount. They were farther away than they should be given their redshift. The universe hadn't been slowing down in the past. It had been expanding more slowly, which meant that now, today, the expansion was faster. The universe wasn't decelerating, it was accelerating. Careful measurements had revealed not the answer to an old question, but the existence of an entirely new mystery, one that would require us to reconsider the fundamental composition of everything that exists. Which leads us naturally to consider what could possibly cause such acceleration, what mysterious force or substance could overpower gravity on cosmic scales. Physicists name the mysterious cause of cosmic acceleration dark energy. Though the name reveals our ignorance rather than our understanding, it's dark because it doesn't emit, absorb, or reflect light. It's energy because it must possess energy density to influence space-time. Beyond these basic facts, dark energy remains perhaps the deepest mystery in modern physics. The simplest explanation for dark energy is Einstein's cosmological constant, the term he added to his equations to create a static universe and later regretted. In this interpretation, dark energy is a property of space itself. Every cubic meter of vacuum possesses a tiny amount of energy, a sort of inherent tension in the fabric of reality. This vacuum energy doesn't dilute as the universe expands. Create more space, and you create more dark energy. As the universe grows larger, dark energy's influence grows stronger relative to matter and gravity. This explanation has the advantage of simplicity and matches observations reasonably well. Match measurements within the margin of error match measurements within the margin of error. Problem solved, or so it might seem. But there's a profound difficulty with this explanation, one so severe that some physicists consider it the worst prediction in the history of science. When quantum physicists calculate what the vacuum energy density should be based on particle physics, they get an answer that's wrong by a factor of 10 to the power of 120. That's not 10 times too large, or even a million times too large. It's one followed by 120 zeros times too large. Imagine predicting that a paperclip would weigh as much as the entire observable universe. That's the scale of the discrepancy. Something is clearly cancelling out almost all of the vacuum energy predicted by quantum theory, leaving only the tiny amount we observe driving cosmic acceleration. But what? And why that specific tiny amount? The precision of this cancellation seems impossibly fine-tuned, like balancing a pencil on its point within the width of an atom. Alternative explanations for dark energy exist, though none are entirely satisfying. Perhaps dark energy isn't constant but changes over time, a dynamic field called quintessence that pervades space and evolves as the universe ages. Perhaps our theory of gravity itself breaks down at cosmic scales, and what appears as dark energy is actually a modification to general relativity. Perhaps we live in a higher dimensional space, and dark energy represents the influence of extra dimensions we cannot perceive. Each of these possibilities has been explored mathematically, searched for observationally, and found either inconsistent with data or unable to explain why the acceleration began when it did. Dark energy stubbornly resists our attempts to understand it. We can measure its effects with increasing precision. We can watch it push galaxies apart. We can predict how it will shape the universe's future, but we cannot say what it actually is. The mystery deepens when we consider dark energy's dominance. Current measurements suggest it accounts for about 68% of the total energy in the universe. Dark matter, the invisible substance that holds galaxies together, makes up about 27%. Ordinary matter, everything made of atoms, from stars to planets to human beings, constitutes less than 5% of the cosmic inventory. We are quite literally a minority component in a universe dominated by things we don't understand. And this connects to something equally important, the specific timing of dark energy's dominance, and what that timing might mean for our ability to observe and understand the cosmos. One of the most puzzling aspects of dark energy isn't just that it exists, but when it came to dominate the universe. For billions of years after the Big Bang, matter and radiation controlled cosmic expansion. Gravity from matter worked to slow the expansion, exactly as Einstein's original equations predicted. Dark energy was always present, but its influence was negligible compared to the density of matter packed into a smaller universe. As space expanded, matter spread out and became less dense. A galaxy that was once close to its neighbours moved farther away as space stretched between them. The gravitational influence of matter weakened, but dark energy, being a property of space itself, didn't dilute. Its energy density remained constant even as the volume of the universe increased. Eventually, about 4 billion years ago, the energy density of dark energy overtook the energy density of matter. This transition marks a fundamental shift in cosmic evolution. Before it, the universe was decelerating, gravity winning the tug-of-war with expansion. After it, the universe began accelerating, dark energy's repulsive effect overwhelming gravity's attractive pull. We happen to live in the era just after this transition, when dark energy's dominance is relatively recent on cosmic timescales. This timing seems oddly convenient, and physicists call it the coincidence problem. The universe is 13.8 billion years old. Dark energy became dominant about 4 billion years ago. If the universe were a 24-hour day, dark energy only took control in the early evening. Why should we happen to exist at precisely the epoch when matter and dark energy have comparable densities? If dark energy had dominated earlier, galaxies might never have formed. The accelerating expansion would have prevented matter from collecting into the dense clumps needed to create stars and planets. If dark energy had dominated much later, we might have missed our observational window. Distant galaxies would already be racing away at speeds approaching light, their light stretched into invisibility. Some physicists suggest this timing isn't coincidence but selection effect. Perhaps we can only observe the universe during epochs when the conditions allow observers to exist. This anthropic reasoning makes some scientists uncomfortable, as it seems to explain a mystery by declaring it inevitable. But it remains one possible answer to why we find ourselves in this particular cosmic moment. Another possibility is that dark energy itself is dynamic, varying in strength over cosmic time. Perhaps it was weaker in the early universe and has been gradually strengthening. Or perhaps it operates in cycles, periods of dominance alternating with periods of dormancy. Some theoretical models suggest dark energy might even reverse its effect in the far future, switching from cosmic acceleration to cosmic contraction. Testing these possibilities requires measuring how dark energy's influence has changed over time. This means looking deeper into space and farther back in time, observing supernovae and galaxies from increasingly distant cosmic epochs. Several major observational projects are underway or planned specifically to map dark energy's history with greater precision. The Dark Energy Survey, conducted from the Cerro Tololo Inter-American Observatory in Chile, spent 6 years mapping hundreds of millions of galaxies to trace how structure in the universe has evolved under dark energy's influence. The European Space Agency's Euclid mission, launched in 2023, is creating the largest three-dimensional map of the universe ever constructed. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey billions of galaxies to measure dark energy's properties with unprecedented accuracy. These observations might reveal that dark energy is indeed Einstein's cosmological constant, unchanging across cosmic time, or they might detect subtle variations that point toward a more dynamic explanation. Either result would be profound. Confirmation of a true cosmological constant would deepen the mystery of why vacuum energy has exactly the tiny value we observe. Detection of variations would open entirely new questions about what dark energy is and how it operates. But there's another layer to consider beyond just measuring dark energy's behaviour. The fundamental question of whether our observations themselves might be misleading us. Science progresses through a cycle of observation, theory, and testing. We observe phenomena, construct theories to explain them, and design new observations to test those theories. When observations contradict expectations, we have two choices: modify the theory or question the observations. The discovery of cosmic acceleration has prompted both responses, and it's worth contemplating whether we might be misinterpreting what we see. The case for dark energy rests primarily on observations of distant Type 1, a supernovae, appearing dimmer than expected. But several factors could potentially explain this dimming without invoking dark energy. Perhaps these ancient supernovae were intrinsically dimmer than modern ones. stellar evolution and chemical composition have changed over billions of years. Early stars formed from nearly pure hydrogen and helium, while later generations incorporated heavier elements created by previous supernovae. These chemical differences might affect how bright Type 1a explosions become. Extensive studies have examined this possibility, comparing supernovae at different distances and cosmic epochs. The results show remarkably consistent brightness across billions of years, suggesting the chemical evolution doesn't significantly affect peak luminosity. But the possibility hasn't been entirely eliminated. Our understanding of supernova physics continues to improve, and subtle effects might yet be discovered. Another possible explanation is extinction by dust. Light travelling billions of years through space passes through enormous quantities of gas and dust between galaxies. Even a small amount of absorption could dim distant supernovae enough to mimic the signature of cosmic acceleration. However, dust affects different wavelengths of light differently, preferentially absorbing blue light while letting red light through. This would change the colour of distant supernovae in ways we don't observe. The dimming appears grey, affecting all wavelengths equally, exactly as expected from increased distance rather than dust. A more exotic possibility is that our local region of the universe is unusual, perhaps sitting in a vast underdense void where matter density is lower than average. In such a void, local expansion might proceed faster than the cosmic average, making distant galaxies appear to be accelerating away when they're actually just receding at the expected rate. This void model would eliminate the need for dark energy, explaining the observations through cosmic geography rather than mysterious new physics. Testing the void hypothesis requires mapping the large-scale structure of the universe in 3 dimensions, looking for evidence of an enormous underdensity centered on our position. Surveys of millions of galaxies have found no such structure. The distribution of matter appears statistically uniform in all directions, ruling out simple void models. More complex versions involving subtle density variations remain possible, but increasingly contrived. Perhaps the most radical possibility is that our theory of gravity itself needs modification. General relativity has passed every test in the solar system and in binary star systems, but these are relatively small-scale environments. Perhaps gravity behaves differently across intergalactic distances, or in the presence of extremely low matter densities. Modified gravity theories have been proposed that reproduce dark energy's effects without requiring any new substance. These modified gravity theories face significant challenges. They must explain not only cosmic acceleration, but also other phenomena attributed to dark matter, such as the motion of galaxies within clusters and the formation of large-scale structure. They must match the predictions of general relativity in all the domains where Einstein's theory has been tested successfully. And they must make testable predictions that distinguish them from dark energy models. So far, no modified gravity theory has successfully met all these requirements. The observations continue to favour dark energy as the simplest explanation consistent with all available data. But the possibility remains that future observations might reveal deviations from general relativity, hints that gravity itself is more complex than we currently understand. The accumulation of evidence from multiple independent sources strengthens confidence in cosmic acceleration as a real phenomenon. Observations of the cosmic microwave background, the afterglow of the Big Bang, show patterns consistent with a universe dominated by dark energy. The distribution of galaxies on the larger scales matches predictions of accelerated expansion. The ages of the oldest stars align with a universe that transitioned from deceleration to acceleration. Each of these observations could potentially be explained in other ways, but explaining all of them without dark energy requires an increasingly baroque collection of alternative assumptions. The principle of Occam's razor suggests favouring the simplest explanation consistent with the data, and despite its profound mystery, dark energy remains the simplest explanation for the cosmic acceleration we observe. And so, we find ourselves at the threshold of a deeper exploration. What exactly have we measured, and how can we be certain that the universe's expansion is truly accelerating? Understanding how we measure cosmic acceleration requires understanding how we measure cosmic distances, and that story begins with a problem that plagued astronomy for centuries. When you look at a star in the night sky, you cannot immediately tell whether it appears dim because it's intrinsically faint or because it's incredibly distant. A nearby candle and a distant searchlight can produce identical apparent brightness, leaving observers unable to distinguish between them without additional information. Henrietta Swan Leavitt solved a crucial piece of this puzzle in the early 1900s while working at the Harvard College Observatory. She studied a class of pulsating stars called Cepheid variables, stars that brighten and dim in regular cycles ranging from days to months. Leavitt discovered a remarkable relationship. The intrinsic brightness of a Cepheid variable star correlates directly with its pulsation period. Longer periods mean brighter stars. This period luminosity relationship transformed Cepheid variables into cosmic yardsticks. Observe a Cepheid's pulsation period and you know its true brightness. Compare that true brightness to its apparent brightness and you can calculate its distance. Edwin Hubble used Cepheid variables in the Andromeda Galaxy to prove it lay far beyond our Milky Way, establishing that the universe contains countless galaxies separated by vast gulfs of space. But Cepheid variables, while useful for measuring distances to nearby galaxies, aren't bright enough to be seen in extremely distant galaxies billions of light years away. For cosmic distances, astronomers needed something far more luminous, something bright enough to be observed across most of the visible universe. Type 1. A supernovae provided exactly this capability. A Type 1a supernova occurs when a white dwarf star, the dense remnant left after a sun-like star exhausts its fuel, accumulates matter from a companion star. White dwarfs are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. This pressure can support a white dwarf up to about 1.4 solar masses, a limit called the Chandrasekhar limit after the physicist who calculated it. When a white dwarf approaches this limit, the core temperature rises until carbon fusion ignites explosively. Unlike the controlled fusion in normal stars, this ignition is catastrophic. Within seconds, the entire star undergoes thermonuclear detonation, releasing energy equivalent to billions of years of normal stellar output. The explosion produces about as much light as an entire galaxy of hundreds of billions of stars, making it visible across cosmic distances. The key insight is that this explosion always occurs at essentially the same mass, the Chandrasekhar limit, making the peak brightness remarkably consistent. Some variation exists due to differences in composition and explosion details, but these variations follow predictable patterns. Astronomers develop techniques to standardize the measurements, correcting for the subtle differences and achieving distance measurements accurate to within a few percent. Finding Type 1. A supernova requires patience and systematic observation. These explosions are rare in any given galaxy, occurring perhaps once every few hundred years. To find enough supernovae for statistical analysis, the supernova search teams monitored thousands of galaxies night after night, comparing new images to archived images and looking for the sudden appearance of new bright points of light. When a candidate supernova appeared, the teams had to work quickly. The brightness rises rapidly to peak over about 2 weeks, then fades over the following months. To measure the peak brightness accurately, observers needed multiple measurements during this window. Scheduling telescope time, coordinating observations from different sites to cover different phases, and analysing the data all had to proceed with urgency. The process required unprecedented international collaboration. Telescopes in Chile, Hawaii, Australia, and other locations around the world participated in the surveys. When one telescope couldn't observe due to weather or scheduling, others continued the watch. The supernova cosmology projects represented some of the largest collaborative efforts in astronomy, involving dozens of researchers across multiple institutions and countries. Let that thought settle as we move forward to understand exactly what these careful observations revealed about cosmic expansion. Every atom emits, and iron produces yet another. These spectral fingerprints let astronomers identify the chemical composition of distant stars and galaxies by analysing the light they emit. But there's something remarkable that happens to these patterns when objects are moving relative to us. Christian Doppler explained the underlying principle in 1842 using sound waves. When a sound source moves toward you, the waves bunch up, raising the pitch. When it moves away, the waves stretch out, lowering the pitch. You hear this effect every time an ambulance passes, the siren shifting from high to low as the vehicle moves from approaching to receding. The same principle applies to light waves, though the effect is called redshift rather than the Doppler effect. When a galaxy moves away from us, the light waves stretch during their journey across space. This stretching shifts the wavelength toward the red end of the spectrum, hence redshift. Shift tells us. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. Shift tells us the recession velocity shift tells us the recession velocity. Greater redshift means faster motion away from us. Edwin Hubble's crucial discovery was that nearly all galaxies show redshift, indicating they're moving away from us, and the amount of redshift increases with distance. Nearby galaxies have small redshifts, indicating modest recession speeds. Distant galaxies have large redshifts, indicating much higher speeds. When Hubble plotted distance against recession velocity, he found a linear relationship: double the distance, double the recession speed. This relationship, known as Hubble's law, provided the first clear evidence that the universe is expanding. But there's a subtle but important point about what expansion means in cosmic terms. Galaxies aren't moving through space away from us. Space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. This distinction matters when we consider very distant objects and very high redshifts. For nearby galaxies, the distinction hardly matters. You can think of redshift as motion through space and get essentially correct results. But for distant galaxies, space has expanded so much during the light's journey that simple Doppler formulas break down. A galaxy with redshift of 1 has had its light wavelengths doubled, which you might interpret as moving away at the speed of light. But actually, such a galaxy is receding faster than light, carried by the expansion of space itself. This seems to violate Einstein's rule that nothing can move faster than light, but it doesn't. The rule applies to motion through space, not the expansion of space itself. Space can expand at any rate, and distant regions of the universe are indeed receding from us faster than light. We cannot see galaxies beyond a certain distance, because their light, though moving toward us at light speed, is being carried away by space expanding faster than the light can make progress toward us. The cosmic microwave background, the oldest light we can observe, comes from material currently about 46 billion light-years away, even though the universe is only about 13.8 billion years old. This apparent paradox resolves when you account for the expansion of space during the light's journey. The material emitted this light when it was much closer to us, but expansion has carried it to its current enormous distance. Understanding redshift as a measure of cosmic expansion rather than simple motion is crucial for interpreting observations of distant supernovae. When the supernova search teams measured redshifts of their target galaxies, they were measuring how much the universe had expanded during the light's journey from supernova to telescope. Higher redshift means the light started its journey. when the universe was significantly smaller. The beauty of comparing redshift with distance is that it reveals the expansion history. If the universe had been expanding at a constant rate, the relationship between distance and redshift would follow a specific mathematical curve. Revealed this bending, this deviation from the standard model revealed this bending, this deviation from constant expansion, and the direction of the bend indicated acceleration rather than deceleration. Measuring this effect required extraordinary precision. The difference between the expected deceleration and the observed acceleration shows up as discrepancy of about 25% in the measured distances to high redshift supernovae. This might sound like a large margin, but systematic errors can easily introduce 25% uncertainties in astronomical measurements. The teams had to eliminate or account for every possible source of error to be confident the effect was real. They checked for dust extinction by measuring supernova colours. They checked for evolutionary effects by comparing supernovae at different redshifts. They checked for selection biases by analysing how they found and chose their supernova sample. They checked for gravitational lensing by examining the distribution of matter between us and the supernova. Every conceivable source of systematic error was investigated, quantified, and either corrected or ruled out. The fact that two independent teams using different telescopes, different analysis techniques, and different supernova samples reached the same conclusion strengthened confidence enormously. When competitors using different methods agree on a surprising result, it's much harder to dismiss as a mistake or artifact. The convergence of evidence from the Supernova Cosmology Project and the High Z Supernova Search Team made cosmic acceleration difficult to ignore, and this connects to something equally important: the other independent lines of evidence that emerged to support the supernova findings. The cosmic microwave background radiation is the oldest light in the universe. Released about 380,000 years after the Big Bang, when the expanding cosmos had cooled enough for atoms to form. Before this moment, the universe was a hot plasma of electrons and nuclei, opaque to light because photons scattered constantly off free electrons. When atoms formed, photons could finally travel freely through space. And this liberation created a flash of light that fills the entire universe. We detect this ancient light today as microwave radiation coming from all directions, cooled by the expansion of space from thousands of degrees to just under 3 degrees above absolute zero. It's the most perfect blackbody radiation ever measured, with a temperature of 2.725 Kelvin and tiny variations of only about 1 part in 100,000 across the sky. These tiny variations, detected first by the Cosmic Background Explorer satellite in the early 1990s, and later with much higher precision by the Wilkinson Microwave Anisotropy Probe and the Planck satellite, contain a wealth of information about cosmic conditions in the early universe. They represent density fluctuations in the primordial plasma, regions slightly hotter and denser than average that would eventually collapse to form galaxies and galaxy clusters. The pattern of these fluctuations follows specific mathematical predictions depending on the universe's composition and geometry. Like sound waves creating harmonics in a musical instrument, density waves in the early universe created a characteristic pattern of hot and cold spots in the cosmic microwave background. The size and amplitude of these patterns depend on several cosmic parameters, including the density of ordinary matter, the density of dark matter, and the density of dark energy. When scientists analysed the cosmic microwave background data, they found something remarkable. The pattern matched predictions for a flat universe, with about 5% ordinary matter, 27% dark matter, and 68% dark energy. This composition matched what the supernova observation suggested, providing independent confirmation from a completely different type of observation, looking at a completely different cosmic epoch. The cosmic microwave background also confirmed the accelerated expansion in another way. The distance to the surface of last scattering, the spherical shell from which the cosmic microwave background photons originated, can be calculated from the angular size of the hot and cold spots. This distance depends on the expansion history of the universe. In a decelerating universe, the distance would be smaller than in an accelerating universe, affecting the apparent size of the spots. The measurements match predictions for an accelerating universe. The spots appeared exactly the size they should if dark energy exists and dominates cosmic dynamics. Once again, an independent line of evidence pointed to the same conclusion. Something is causing the expansion of space to accelerate. Additional confirmation came from observations of baryon acoustic oscillations, a pattern imprinted in the distribution of galaxies by sound waves in the early universe. Before atoms formed, pressure waves rippled through the plasma, and these waves left an imprint on where matter concentrated. Galaxies today show a subtle preference for separating by about 490 million light-years. The distant sound waves could travel in the early universe before atoms formed and the pressure stopped. This preferred separation acts as another standard ruler, a known length scale that appears at different angular sizes depending on distance and expansion history. Surveys measuring galaxy positions have detected this baryon acoustic oscillation signal and used it to map cosmic expansion. Like the cosmic microwave background and supernovae, baryon acoustic oscillations indicate an accelerating universe dominated by dark energy. The convergence of evidence from these three independent methods, Type 1 supernovae, cosmic microwave background radiation, and baryon acoustic oscillations, creates compelling support for cosmic acceleration. Each method has different systematic uncertainties and potential sources of error. The fact that all three agree makes it extremely unlikely that the result is an artifact or mistake. Scientists often talk about combining evidence from multiple independent sources as breaking degeneracies. A single measurement might be consistent with several different explanations. A second measurement might also be consistent with several explanations, but not the same ones. When you combine measurements, the set of explanations consistent with all observations shrinks dramatically. The combination of supernova, cosmic microwave background, and baryon acoustic oscillation data leaves dark energy as essentially the only explanation consistent with everything we observe. This doesn't mean dark energy is certainly correct. New observations might yet reveal flaws in our interpretation, or point toward alternative explanations, but the burden of proof has shifted. Any alternative to dark energy must explain not just one anomalous observation, but a convergent pattern of evidence from multiple independent sources spanning different cosmic epochs and measuring different physical phenomena. Building on this foundation, we can now explore what these measurements tell us about the universe's past, present, and future expansion history. The universe has gone through several distinct phases of expansion, each dominated by different components of the cosmic energy budget. Understanding this history helps us comprehend how we arrived at the current epoch of dark energy dominance and what might lie ahead. In the beginning, during the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion called cosmic inflation. Space expanded exponentially, doubling in size every tiny fraction of a second. In less than 1/billionth of a trillionth of a trillionth of a second, a region smaller than an atom grew to the size of a marble, then to the size of Earth, then far larger. This inflation solved several problems with the standard Big Bang model, and created the initial density fluctuations that eventually became galaxies. Inflation ended when the energy driving it decayed into ordinary matter and radiation. This reheating created a hot, dense universe filled with particles and photons. For the next several 100,000 years, radiation dominated cosmic expansion. Photons, despite having no mass, carry energy and therefore contribute to the universe's total energy density. In the early universe, radiation was so dense and energetic that it controlled expansion dynamics. During this radiation-dominated era, the universe expanded and cooled. Quarks combined to form protons and neutrons. Protons and neutrons fused to create the first light element nuclei, primarily hydrogen and helium with traces of lithium. The cosmic microwave background was born when electrons finally combined with nuclei to form neutral atoms, allowing photons to travel freely. As expansion continued, radiation's energy density decreased faster than matter's energy density. Radiation dilutes as the universe expands because the number of photons spreads over a larger volume, and each photon's wavelength stretches, reducing its energy. Matter's energy density dilutes more slowly because while the number of particles spreads over a larger volume, each particle's mass remains constant. About 50,000 years after the Big Bang, matter's energy density overtook radiation's energy density, beginning the matter-dominated era. From this point forward, matter controlled cosmic expansion. Gravity from the combined mass of ordinary matter and dark matter worked to slow the expansion. The denser regions of matter began collapsing under their own gravity, forming the first stars and galaxies. For billions of years, matter dominated. Galaxies assembled from smaller building blocks. Stars formed, lived, and died, creating heavy elements. Galaxy clusters grew as gravity pulled galaxies together. The expansion continued, slowing gradually. Exactly as Einstein's equations predicted for a matter-dominated universe. Then, about 4 billion years ago, something changed. The energy density of matter had decreased enough through expansion that dark energy's constant energy density became dominant. The universe entered its current phase, the dark energy-dominated era. Expansion began accelerating. Gravity still pulls galaxies together locally, but on the larger scales. Dark energy pushes space apart with increasing vigour. We can map this expansion history by measuring how fast the universe was expanding at different times in the past. Looking at distant objects means looking back in time, because light takes time to travel across space. A galaxy 10 billion light-years away appears as it was 10 billion years ago. By measuring the redshifts and distances of objects at various distances, we reconstruct the expansion rate at different cosmic epochs. The supernova data revealed this history clearly. High redshift supernova, from epochs when the universe was younger and denser, showed the expected deceleration. Intermediate redshift supernova, from around the transition epoch, showed the changeover from deceleration to acceleration. Low redshift supernova, from recent epochs, showed clear acceleration. This transition from deceleration to acceleration is one of the most significant events in cosmic history, comparable to the transitions from inflation to radiation dominance or radiation dominance to matter dominance. Each transition fundamentally altered how the universe evolved and what structures could form. Consider what would have happened if dark energy had dominated earlier. If the transition occurred, say, 1 billion years after the Big Bang instead of 10 billion years after, the accelerating expansion would have begun before most galaxies formed. Gravity wouldn't have had time to pull matter together into the dense concentrations needed for stars and galaxies. The universe might have remained forever a thin, cold, empty expanse of isolated atoms. Conversely, if dark energy was slightly weaker, or the transition occurred later, we'd still be in a decelerating phase. Expansion would be slowing, perhaps heading toward an eventual big crunch. The ultimate fate of the universe would be to collapse back to a singularity, rather than expand forever into cold, dark emptiness. The actual history we observe, with dark energy becoming dominant about 10 billion years after the Big Bang, allowed galaxies to form but ensures they'll eventually be separated by ever-increasing distances. In a sense, we live in a privileged epoch, late enough for complex structures to have formed but early enough to observe distant galaxies before they recede beyond our cosmic horizon. And this brings us to something equally remarkable. What observations are revealing about dark energy's properties, and whether it truly is constant or might be evolving over time? One of the most important questions in cosmology is whether dark energy's density remains constant as the universe expands or whether it changes over time. This question matters enormously because it distinguishes between different theoretical explanations for dark energy and determines the universe's ultimate fate. If dark energy is Einstein's cosmological constant, its energy density never changes. Each cubic meter of space contains exactly the same amount of dark energy today as it did 10 billion years ago and will contain 10 billion years in the future. As the universe expands and creates more cubic meters of space, the total amount of dark energy increases, but the density remains fixed. This leads to an exponentially accelerating expansion that continues forever. If dark energy is something more dynamic, perhaps a quantum field pervading space called quintessence, its density might evolve over cosmic time. It could be increasing, making the acceleration stronger in the future. It could be decreasing, leading to a future where matter dominates again and expansion decelerates. It might even become negative, creating cosmic contraction and eventual collapse. Distinguishing these possibilities requires precise measurements of how dark energy's influence has changed over billions of years. This means observing objects at various distances and redshifts, mapping out the exact expansion history in detail. Small deviations from the predictions of a cosmological constant would indicate dynamic dark energy. The parameter cosmologists use to characterize dark energy's behavior is called the equation of state, denoted by the letter d. This parameter relates dark energy's pressure to its energy density. For Einstein's cosmological constant, W equals exactly -1. For other forms of dark energy, W might differ from -1 and might change over time. Why does this matter? In ordinary matter, pressure is positive. The air in a balloon pushes outward on the walls, but dark energy has negative pressure, meaning it pulls inward on itself while somehow causing space to expand outward. This seems contradictory until you work through Einstein's equations carefully and realize that negative pressure creates a sort of gravitational repulsion, pushing space apart. The exact value of W determines how strong this repulsion is. If W is more negative than -1, dark energy exerts even stronger repulsion than a cosmological constant. If W is less negative than -1 but still negative, the repulsion is weaker. If W equals 0, you have matter-like behavior with no acceleration. Positive W would create cosmic deceleration. Current observations constrain W to be very close to -1, consistent with a cosmological constant within measurement uncertainties. The combination of supernova data, cosmic microwave background measurements, and baryon acoustic oscillations gives W equals -1.0 plus or minus about 0.1. This is consistent with a pure cosmological constant, but doesn't rule out small deviations. Some studies have hinted at possible evolution in W over cosmic time, with dark energy perhaps being slightly more negative in the past and less negative today. If confirmed, this would be revolutionary, ruling out the cosmological constant and requiring new physics to explain dark energy's dynamics. But the evidence remains marginal. Next generation of dark energy experiments. The goal is to measure the energy density of the universe to a precision of 1 part in 100,000. This would allow us to determine whether the universe is dominated by dark energy or dark matter. The results of these experiments will have a profound impact on our understanding of the universe and our place in it. Next generation of dark energy experiments aims to measure W to within about 1% uncertainty and detect any evolution in W over cosmic time. The Nancy Grace Roman Space Telescope will observe thousands of Type I supernovae across a range of redshifts. The Dark Energy Spectroscopic Instrument is mapping millions of galaxies to trace baryon acoustic oscillations with unprecedented precision. The European Euclid mission is measuring both cosmic shear the distortion of galaxy images by intervening matter, and galaxy clustering to constrain dark energy's properties. These projects represent investments of hundreds of millions of dollars and decades of effort by thousands of scientists worldwide. The scale of the enterprise reflects the profound importance of the question. Understanding dark energy means understanding what constitutes 70% of the universe and what will determine its ultimate fate. If dark energy truly is a cosmological constant, the future is relatively clear, if somewhat melancholy. The acceleration will continue forever, eventually separating galaxy clusters so far that each will exist in its own isolated pocket of space, unable to see other clusters because the space between them expands faster than light can cross it. Stars will age and die. Black holes will evaporate. The universe will end in a cold, dark, empty state called heat death. If dark energy evolves and strengthens, the ending might come sooner and more dramatically. In a scenario called the Big Rip, dark energy's repulsion grows so strong that it eventually tears apart galaxy clusters, then galaxies, then stars, then planets, and finally atoms themselves. Everything gets ripped apart by space expanding infinitely fast in finite time. If dark energy weakens or reverses, the universe might eventually collapse in a big crunch, all matter falling back together into a singularity. This might even lead to a cyclic universe. Big bangs followed by big crunches in eternal succession, though such scenarios face severe theoretical difficulties. The observations currently favour a cosmological constant and eternal acceleration, but the uncertainties remain large enough that other possibilities cannot be excluded. We stand at a moment in scientific history where the next generation of observations might definitively answer one of humanity's oldest questions. How will the universe end? Let that thought settle as we move forward to contemplate what the acceleration means for the universe's large-scale structure and future evolution. The accelerating expansion of the universe creates something called a cosmic event horizon, a boundary beyond which events can never be observed no matter how long we wait. This horizon exists because space in distant regions is expanding faster than light can travel through it, creating an insurmountable barrier to observation and communication. Imagine a galaxy currently 15 billion light-years away. Light leaving that galaxy travels toward us at the speed of light, covering about 1 light-year of distance per year. But the space between us and that galaxy is expanding, adding perhaps 2 light-years of distance per year. The light makes progress toward us, but not enough progress to overcome the expansion carrying the galaxy away. The photons are like someone climbing up a down escalator that's moving faster than they can climb. For distant enough galaxies, this tug-of-war means light emitted today will never reach us. There exists a distance currently about 16 billion light-years, beyond which objects are receding so fast that light cannot make the journey to Earth even given infinite time. This boundary is the cosmic event horizon, and it will shrink as the acceleration continues. In the far future, galaxies currently within our observable universe will cross this horizon and disappear from view. Their light will become so redshifted that the wavelengths stretch to kilometers, then light-years, effectively vanishing. The last photons from these galaxies will arrive weakened and stretched, then no more will come. The galaxy will have crossed an invisible boundary in space beyond which we are forever separated. This horizon is different from the better-known cosmological horizon, the boundary of the observable universe set by the finite age of the universe and the finite speed of light. We cannot see beyond the cosmological horizon because light from more distant regions hasn't had time to reach us yet. But in principle, we'll eventually see more as light from farther regions arrives. The cosmic event horizon works differently. Objects beyond it are forever invisible, not because light hasn't arrived yet, but because it never will. The existence of this horizon raises philosophical questions about knowledge and reality. If events beyond the horizon cannot affect us in any way, cannot be observed even in principle, Do they matter? Is the universe beyond our horizon real in any meaningful sense? These questions mirror debates about whether regions inside black holes are real. Given that information from inside the event horizon cannot escape to the outside universe, most physicists accept that the unobservable universe is real, that galaxies continue to exist even after they cross our event horizon. The laws of physics don't change at the horizon. Space doesn't have a physical boundary there. The horizon is an observational limitation for us, not a fundamental feature of the cosmos itself. But the horizon does create interesting constraints on what we can ever know. As time passes and more galaxies cross the horizon, the observable universe will contain less and less matter. Distant galaxy clusters will fade from view. Eventually, only our local group of gravitationally bound galaxies will remain visible. An island of matter in an expanding void. Astronomers in the far future will observe a very different universe than we see today. They'll see a few nearby galaxies in a vast dark emptiness. If they try to measure the cosmic expansion using distant galaxies, they'll find none to measure. The cosmic microwave background will have redshifted into invisibility. Its photons stretch to wavelengths longer than the observable universe itself. This raises an unsettling possibility. Perhaps we're already in such a situation. Perhaps there are phenomena and structures beyond our current cosmic horizon that previous generations of observers could have seen, but we cannot. Expansion in the first fraction of expansion in the first fraction of a second after the Big Bang would have created a universe far larger than the observable region. Most of that inflated space lies beyond our horizon, forever inaccessible to observation. We see only a tiny bubble within a vastly larger cosmos. This connects to something equally important, how the cosmic horizon affects our ability to test fundamental physics and whether there might be ways to glimpse beyond it. While dark energy dominates cosmic expansion on the larger scales, its influence on individual galaxies and galaxy clusters is surprisingly subtle. Understanding this subtlety requires understanding how different forces compete at different scales, and why some structures resist the cosmic acceleration, while others succumb to it. Gravity holds galaxies together. The stars, gas, and dark matter in a galaxy orbit the galactic center, bound by mutual gravitational attraction. The Milky Way, for instance, has a mass of roughly 1 trillion times the Sun's mass concentrated within a region about 100,000 light-years across. This creates strong gravity that easily overwhelms dark energy's repulsive effect on these scales. Similarly, galaxy clusters remain gravitationally bound despite the cosmic acceleration. The Virgo cluster, our nearest major galaxy cluster, contains about 2,000 galaxies within a region, roughly 10 million light-years across. The combined gravity of all this matter holds the cluster together, preventing dark energy from pulling it apart. Galaxies within the cluster orbit the cluster's center, sometimes colliding and merging, indifferent to the acceleration of cosmic expansion happening in the vast voids between clusters. But consider the space between galaxy clusters. Here, matter is sparse, gravity weak, and dark energy's influence dominant. This space expands steadily, pushing clusters apart. Clusters that are not already gravitationally bound to each other will never become bound because the space between them expands faster than gravity can pull them together. This creates a fundamental division in the universe's future. Gravitationally bound structures will remain bound, their internal dynamics determined by gravity rather than cosmic expansion. The Milky Way and Andromeda Galaxy are currently approaching each other at about 100 kilometers per second and will eventually collide and merge. Despite the cosmic acceleration, this collision happens because the galaxies are close enough that their mutual gravity overwhelms the expansion of space between them. However, galaxy clusters not already gravitationally bound to our local group will recede forever. The Coma cluster, about 300 million light-years away, will grow increasingly distant as space expands between us. Eventually. It will cross our cosmic event horizon and disappear from view entirely. The galaxies in that cluster will continue their existence, but they'll be forever beyond our ability to observe or interact with. This division between bound and unbound structures means dark energy creates isolated islands of matter in an ever-expanding void. Each island consists of a gravitationally bound galaxy cluster or group that will remain intact. Between the islands, space expands without limit, making the cosmic void ever emptier and darker. Within our local bound structure, the future holds interesting developments. The Milky Way and Andromeda will merge in about 4 billion years, creating a giant elliptical galaxy sometimes called Milkomeda. The collision will dramatically rearrange both galaxies, triggering bursts of star formation as gas clouds collide and compress. Some stars will be flung into intergalactic space. Others will settle into new orbits around the merged galaxy's centre. After this merger, the local group will likely settle into a relatively stable configuration. The remaining smaller galaxies in the group will either merge with Milkomeda or become satellites orbiting it. Star formation will continue for billions of years as gas reserves are converted into stars, but eventually the gas will be exhausted. Star formation will cease. The galaxy will gradually darken as massive stars age and die, while lower mass stars continue burning for trillions of years. This eventual fate of a dark, quiet galaxy surrounded by expanding emptiness is the destiny of all gravitationally bound structures in an accelerating universe. The timeline is almost incomprehensibly long. The universe is currently about 13.8 billion years old. The first stars have been dying for over 13 billion years, but the last stars won't exhaust their fuel for 100 trillion years or more. We're witnessing the very early stages of a story that will unfold over timescales that dwarf all of recorded history. Dark energy also affects structure formation in more subtle ways. New large-scale structures cannot form once the universe becomes dark energy dominated because the acceleration prevents matter from collecting across large distances. We observe enormous filaments and sheets of galaxies, cosmic web structures that formed when matter dominated. These are essentially the largest structures that will ever form. No new galaxy superclusters will assemble. The universe has finished building its largest constructions. This means astronomers today can observe a richer universe than future generations will see. We can study the cosmic web, observe distant galaxy clusters, measure the large-scale structure that traces back to tiny fluctuations in the cosmic microwave background. Future astronomers in the far distant future will see only their local galaxy island, knowing nothing of the vast cosmic architecture that once existed within their horizon. Building on this understanding, we can now explore how dark energy interacts with another mysterious component of the universe: dark matter. The universe contains two distinct _4 components: dark matter and dark energy, and while their names are similar, they represent completely different phenomena. Understanding both is essential to understanding modern cosmology, and the interplay between them shapes cosmic evolution. Dark matter was discovered through its gravitational effects on visible matter. In the 1930s, Fritz Zwicky noticed that galaxies in the Coma cluster were moving too fast. The cluster should fly apart if the visible matter were all that existed. Something invisible was providing extra gravity to hold the cluster together. In the 1970s, Vera Rubin measured the rotation of individual galaxies and found stars orbiting faster than they should based on the visible matter. Again, invisible matter was implied. These observations led to the dark matter hypothesis. Galaxies and galaxy clusters contain large amounts of matter that doesn't emit, absorb, or reflect light. This matter interacts through gravity but not through electromagnetism, making it invisible to telescopes. Current estimates suggest dark matter outweighs ordinary matter by about 5-1. Most of the matter in the universe is dark. Dark matter's composition remains unknown. It's not made of ordinary atoms, as we can account for all the atomic matter through various observations. It could be exotic particles predicted by theories extending the standard model of particle physics, such as weakly interacting massive particles or axions. Despite extensive searches, no dark matter particles have been definitively detected in laboratory experiments. Dark energy, by contrast, was discovered through its effect on cosmic expansion rather than through gravitational attraction. Where dark matter clumps and clusters, helping form galaxies and holding them together, dark energy distributes uniformly throughout space, pushing everything apart. Where dark matter is matter-like, dark energy resembles a negative pressure field, or a property of vacuum itself. The two dark components have opposite effects on cosmic expansion. Dark matter's gravity works to slow expansion, pulling matter together. Dark energy's repulsion works to accelerate expansion, pushing space apart. Early in cosmic history, dark matter dominated and expansion decelerated. Later, dark energy took over and expansion accelerated. The transition between these regimes occurred when the energy density of dark matter, diluted by expansion, fell below the constant energy density of dark energy. This interplay shaped the universe's structure. In the matter-dominated era, dark matter collected into vast halos, gravitational wells into which ordinary matter fell. The ordinary matter could radiate energy and cool, settling into the centres of these halos and forming galaxies. Dark matter provided the gravitational scaffolding on which galaxies and galaxy clusters assembled. Dark energy, meanwhile, worked against structure formation on the larger scales. It prevented matter from collecting across truly cosmic distances, creating a scale above which structures cannot form. This scale depends on dark energy's strength and when it came to dominate. In our universe, structures smaller than a few 100 million light-years could form, but larger ones could not. The combination of dark matter and dark energy creates a universe with a specific character, clustered on small to medium scales, with galaxies and galaxy clusters separated by enormous voids and expanding with acceleration on the larger scales. Different ratios of dark matter to dark energy would create very different universes. If dark energy were stronger, it might have prevented any structure formation at all. Galaxies might never have assembled from the primordial matter. If dark energy were weaker or absent, the universe might have recollapsed before stars could form. The specific values we observe allow just enough time for complexity to emerge before acceleration began driving structures apart. This apparent fine-tuning troubles some physicists. Why should the universe have just the right amount of dark energy to allow structure formation, but not too much to prevent it? Why should dark energy become dominant at roughly the same epoch when life capable of observing it would exist? These questions lead to controversial ideas about multiverses and anthropic selection, suggesting we observe these particular values because they're necessary for observers to exist. Alternatives to this anthropic reasoning exist. Perhaps dark energy's value is determined by some undiscovered physical principle that makes it inevitable. Perhaps the value we measure is actually highly probable given correct but unknown laws of physics. The question remains open and actively debated. Research continues on both dark components. Experiments deep underground search for dark matter particles. Particle accelerators try to create dark matter in high-energy collisions. Telescopes map dark matter's distribution through gravitational lensing, observing how its gravity bends light from background sources. Each approach offers different clues about dark matter's nature. Similarly, multiple approaches probe dark energy. Surveys measure cosmic expansion history. Observations test whether dark energy's influence has changed over time. Theorists develop models that might explain dark energy's origin and properties. The convergence of these efforts aims to transform dark energy from an observed phenomenon into understood physics. The fact that our universe contains two major components we don't understand is both humbling and exciting. Humbling because it reminds us how much we still don't know about reality. Exciting because it suggests major discoveries await, potentially revolutionizing our understanding of physics and cosmology. And this raises a gentle question worth exploring. What theoretical frameworks might explain dark energy, and how do they connect to other unsolved problems in physics? Physicists have proposed numerous theoretical explanations for dark energy, ranging from conservative extensions of known physics to radical reimaginings of space, time, and quantum mechanics. Exploring these theories illuminates both the creativity of theoretical physics and the profound challenges dark energy presents. The simplest explanation, as mentioned earlier, is Einstein's cosmological constant, representing the energy density of empty space itself. In quantum field theory, vacuum isn't truly empty, but seethes with virtual particles constantly appearing and disappearing. These quantum fluctuations contribute energy to space, and this vacuum energy might manifest as dark energy. The problem is that calculations predict vacuum energy about 10 to the power of 120 times larger than what we observe, the worst prediction in physics. This vacuum catastrophe suggests either that our calculation is fundamentally wrong, or that some unknown mechanism cancels most of the vacuum energy. Supersymmetry, a theoretical framework that pairs every known particle with a heavier partner, might provide such a cancellation. In supersymmetric theories, contributions from particles and their superpartners cancel almost perfectly. But supersymmetry requires precise fine-tuning to leave exactly the small amount of dark energy we observe, and experiments at the Large Hadron Collider have found no evidence for supersymmetric particles. Another approach involves quintessence, a dynamic field that pervades space and changes over time. Unlike the cosmological constant, quintessence field energy can vary, potentially explaining why dark energy density happens to be comparable to matter density in our epoch. Various quintessence models have been proposed, each with different predictions for how dark energy should evolve. So far, observations haven't detected any evolution, constraining but not eliminating quintessence models. Some theories suggest dark energy might be related to extra dimensions of space. In our everyday experience, space has 3 dimensions: length, width, and height. But some theories of quantum gravity predict additional spatial dimensions too small to observe directly. The dynamics of these extra dimensions might manifest as dark energy in our 3-dimensional experience. String theory, which requires 10 total dimensions, offers frameworks where dark energy emerges from the geometry of hidden dimensions. Modified gravity theories provide a different approach, suggesting that general relativity itself breaks down at cosmic scales. Perhaps gravity becomes slightly repulsive at enormous distances, creating apparent acceleration without requiring dark energy. Various modified gravity theories have been proposed, with names like F of R gravity, DGP gravity, and Galilean theories. Each modifies Einstein's equations in specific ways and makes predictions that can be tested observationally. The challenge for modified gravity theories is that they must reproduce all the successes of general relativity while explaining dark energy. General relativity has passed every test in the solar system, in binary star systems, and in gravitational wave observations. Modified theories must match these results while only deviating at cosmological scales. This proves mathematically difficult, and most modified gravity theories have been ruled out by observations. Another speculative idea involves the cosmological constant varying across different regions of a vast multiverse. In this view, our universe is one bubble in an infinite cosmic foam, each bubble with different values of physical constants. Most bubbles have values of the cosmological constant that prevent structure formation or lead to rapid collapse. We necessarily observe a bubble with a value allowing our existence, explaining the apparent fine-tuning through selection bias rather than fundamental physics. This multiverse explanation troubles many physicists because it seems untestable. If we can never observe other universes, how can we verify they exist? How can we use them to explain observations in our universe? Some argue this represents the end of physics as a predictive science, replacing detailed predictions with anthropic reasoning. Others counter that the multiverse might make testable predictions about the statistical distribution of parameters we can observe. A more radical possibility is that dark energy signals a breakdown in our understanding of time and causality. Some theories suggest the universe might be fundamentally holographic, with three-dimensional experience emerging from information encoded on the two-dimensional boundary. In such frameworks, dark energy might reflect fundamental limits on information density in space. Or perhaps dark energy relates to quantum entanglement across cosmic distances. Recent work in quantum gravity suggests space itself might emerge from entanglement of quantum degrees of freedom. Changes in this entanglement structure might manifest as dark energy. These ideas remain highly speculative, far from making concrete predictions that can be tested observationally. Despite the abundance of theoretical ideas, none has achieved the status of a clearly correct explanation for dark energy. Each theory has attractive features, but also significant problems or unknowns. The situation resembles physics in the early 20th century before quantum mechanics and relativity, when multiple competing frameworks attempted to explain new observations. History suggests this confusion might precede a major breakthrough. Dark energy might be telling us something profound about the nature of space, time, quantum mechanics, or gravity. The solution might require concepts we haven't yet imagined, mathematics we haven't yet developed, or experimental techniques we haven't yet invented. The deeper we look, the more we discover how dark energy connects to other unsolved problems in fundamental physics, the nature of quantum gravity, the hierarchy problem of particle physics, the cosmological constant problem, the nature of time, the measurement problem in quantum mechanics. Perhaps these problems are related, different facets of a single deep mystery about how reality works. There's a kind of peace in accepting that we might be at the frontier of knowledge, that the questions we're asking might not have answers in terms of concepts we currently understand. The universe has surprised us before. Quantum mechanics defied classical intuition. General relativity revealed space-time as dynamic. Quantum field theory united particles and forces in unexpected ways. Dark energy might herald an equally revolutionary shift in how we understand physical reality. Let's rest here for a moment with this thought, before exploring how observations are becoming more precise and what we hope to learn from next-generation experiments. The current generation of dark energy experiments has established cosmic acceleration as a real phenomenon and constrained dark energy's properties to within about 10%. The next generation aims to improve precision by factors of 10 or more, potentially detecting subtle variations in dark energy's behavior that would point towards specific theoretical explanations. The Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, represents a major leap in dark energy observation capability. Scheduled to launch in the mid-2020s, Roman will have a primary mirror similar in size to Hubble's, but with a field of view 100 times larger. This wide-field capability enables efficient surveys of millions of galaxies and thousands of supernovae. Roman's supernova survey will observe Type 1, a supernova across a wide range of redshifts, from nearby explosions in our cosmic neighbourhood to extremely distant ones from when the universe was less than half its current age. By mapping the expansion history in detail across this entire range, the mission will test whether dark energy's density has remained constant or evolved over time. Any detected evolution would rule out the cosmological constant and point toward dynamic dark energy. The telescope will also measure weak gravitational lensing, the subtle distortion of galaxy shapes by intervening matter. Dark energy affects how rapidly structure grows over cosmic time, and these growth rates can be measured through weak lensing. By combining expansion history from supernovae with structure growth history from weak lensing, Roman will provide two independent probes of dark energy's properties. The Dark Energy Spectroscopic Instrument, already operating at Kitt Peak National Observatory in Arizona, is measuring the positions of 35 million galaxies and quasars. By mapping the three-dimensional distribution of matter in unprecedented detail, DESI will detect baryon acoustic oscillations across a wide range of cosmic epochs. The observations will measure how the expansion rate has changed over the past 11 billion years. DESI's measurements are particularly powerful because they probe a different aspect of dark energy than supernovae. Where supernovae measure distances directly, baryon acoustic oscillations measure the expansion rate by tracking how a known length scale appears at different redshifts. The combination of independent methods helps eliminate systematic errors and provides cross-checks on the results. The European Space Agency's Euclid mission, launched in 2023, is conducting the largest three-dimensional mapping of galaxy positions ever attempted. Euclid will observe 2 billion galaxies, measuring their positions, shapes, and redshifts. Like Roman, Euclid will use both baryon acoustic oscillations and weak gravitational lensing to probe dark energy. Euclid's wide survey area covers more than a third of the sky, providing a cosmic census of unprecedented scope. The mission will trace how structure has grown over the past 10 billion years, testing whether gravity behaves as general relativity predicts on cosmic scales. Any deviation would suggest modified gravity rather than dark energy might explain the acceleration. Ground-based facilities are also contributing. The Vera C. Rubin Observatory in Chile will begin operations in the mid-2020s, conducting the legacy survey of space and time. This 10-year survey will observe the entire southern sky every few nights, discovering thousands of supernovae and billions of galaxies. This sheer volume of data will enable statistical studies of dark energy's effects on structure formation and expansion history. These projects represent coordinated international efforts involving thousands of scientists, engineers, and technicians. The investment runs into billions of dollars collectively, reflecting both the importance of dark energy to cosmology and the technical challenges of making precision measurements across billions of light years. Beyond these major missions, numerous smaller experiments target specific aspects of dark energy. The Dark Energy Survey, which completed observations in 2019, measured weak lensing, galaxy clustering, and supernova distances in a coordinated way that allowed cross-checks between methods. Future surveys will build on these techniques with improved precision. Cosmic microwave background experiments continue improving measurements of the early universe. The Simons Observatory and CMB-S4 project will measure the cosmic microwave background polarization with unprecedented sensitivity, probing conditions in the first fraction of a second after the Big Bang. These measurements constrain how dark energy might have affected very early cosmic evolution. Gravitational wave observatories offer a completely independent probe. When black holes or neutron stars merge, they emit gravitational waves that carry information about cosmic distances. By detecting gravitational waves from mergers and measuring the redshifts of the host galaxies, astronomers can construct a distance ladder independent of the traditional electromagnetic methods. This provides yet another check on expansion history measurements. The convergence of multiple independent methods is key to building confidence in results. Each method has different systematic uncertainties and potential sources of error. When multiple methods agree, it becomes increasingly unlikely that all have made the same mistake. The agreement strengthens confidence that we're measuring something real about the universe rather than artifacts of our instruments or analysis techniques. Looking further ahead, even more ambitious projects are being discussed. A concept called the Big Bang Observer would use space-based gravitational wave detectors to observe the universe's earliest moments. Another idea involves building optical interferometers in space, capable of measuring cosmic expansion to 1% precision. These remain decades away, but they illustrate the community's commitment to understanding dark energy. The accumulating data from current and future experiments will test dark energy theories ruthlessly. Models that make specific predictions about how dark energy should vary over time will be confirmed or ruled out. The parameter space available for theoretical speculation will shrink as precision improves. Within perhaps a decade or two, we might have enough data to distinguish between the cosmological constant and various dynamic dark energy models. Of course, the universe might have more surprises waiting. Every time we've improved observational capabilities, we've discovered something unexpected. Perhaps dark energy will reveal additional complexity not captured by current theories. Perhaps we'll find evidence for modified gravity, extra dimensions, or phenomena we haven't yet imagined. The history of science suggests humility. The universe is under no obligation to be comprehensible through the theories we've developed so far. And this is where our journey takes an interesting turn, as we begin contemplating the deeper implications of cosmic acceleration for our understanding of the universe and our place in it. If dark energy is truly Einstein's cosmological constant across time and space, the universe's future is determined. And it's a future quite different from anything our ancestors imagined. Understanding this fate requires thinking on timescales that dwarf all of human experience, that stretch from billions to trillions to genuinely infinite years into a future we can scarcely imagine. In the near term, meaning the next several billion years, the local universe will look relatively familiar. Stars will continue forming in galaxies. Stellar evolution will proceed as it has for billions of years already. The Milky Way and Andromeda will collide and merge in 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. The Milky Way and Andromeda will collide and merge. Life on Earth, if any remains, will face the sun's gradual brightening as it ages, eventually becoming a red giant that engulfs the inner planets. But on the larger scales, changes will be dramatic. Galaxy clusters not already gravitationally bound to our local group will recede beyond the cosmic event horizon. The Virgo cluster, currently our nearest major neighbouring cluster, will disappear from view within about 150 billion years. The Coma cluster, farther away, will vanish sooner. One by one, the familiar galaxies catalogued by astronomers will redshift into invisibility. The cosmic microwave background will also fade away. Currently at about 3 degrees above absolute zero, it will cool as the universe expands, dropping below 1 degree, then 1/10 of a degree, eventually becoming undetectable. Astronomers of the far future will have no way to observe this crucial evidence of the Big Bang. Within about 1 trillion years, star formation will largely cease in our local galaxy. The gas needed to create new stars will be exhausted, already incorporated into existing stars or expelled from the galaxy. The galaxy will enter old age, populated only by long-lived stars and the remnants of stars that have already died. White dwarfs, neutron stars and black holes. Stars already burning will continue for a while longer. Red dwarf stars, the smallest and longest lived, can burn for 10 trillion years or more. The universe is currently less than 14 billion years old, so the first generation of red dwarfs is still in early youth. But eventually, even these miserly stars will exhaust their fuel, fading to black dwarfs, dark cinders too small to have sustained fusion, but too large to have dispersed. By 100 trillion years, virtually all stellar processes will have ceased. The universe will enter what's sometimes called the degenerate era, dominated by stellar remnants rather than active stars. White dwarfs and neutron stars will cool slowly, radiating their residual heat into the ever-expanding void. Black holes will sit quietly in the darkness, slowly evaporating through a quantum process called Hawking radiation. This evaporation is extraordinarily slow. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. Supermassive black holes and galaxy centres would take even longer, 10 to the power of 100 years or more. But given infinite time, even these monuments to gravitational collapse will eventually vanish in a faint spray of particles. After the black holes evaporate, the universe will contain only a thin sea of fundamental particles, electrons, positrons, neutrinos, and photons, all separated by ever-increasing distances as space continues expanding. The temperature will approach absolute zero. No structure will remain, no complexity, no possibility of life or consciousness as we understand it. This is the heat death of the universe, a state of maximum entropy where no useful energy remains to drive any processes. It's the thermodynamic endpoint toward which the second law of thermodynamics inexorably drives isolated systems. In a sense, the universe runs down like a clock, and dark energy ensures it can never wind back up. Some physicists find this fate depressing, the ultimate futility of all existence, all the complexity that emerged from the Big Bang, all the stars and galaxies and life, merely temporary structures that will eventually dissolve into cold, dark nothingness. Every achievement, every thought, every moment of joy or sorrow, ultimately meaningless against the backdrop of eternal heat death. Others find a strange peace in it. The universe had a beginning and will have an end, a complete story with a beginning, middle, and conclusion. The heat death is as natural a conclusion as any other, the universe settling into its lowest energy state and resting there forever. There's something fitting about entropy having the final word, about the cosmos ending not in catastrophe, but in quiet stillness. Of course, this assumes dark energy remains constant. If it evolves and strengthens, the ending might come much sooner in a big rip. If it weakens or reverses, the universe might recollapse. If new physics emerges at very late times, entirely unexpected phenomena might occur. The far future is necessarily more uncertain than the recent past, because we are extrapolating further from what we can observe. But based on our best current understanding, heat death seems the most likely ultimate fate. The universe will expand forever, cooling forever, diluting forever, until nothing remains but isolated particles in an infinite dark void. The journey from the hot, dense beginning to the cold, empty end will have taken infinite time. A span that makes the current age of the universe, 13.8 billion years, seem like the blink of an eye at the start of a story with no end. In contemplating such vast timescales and such a final ending, we might feel our own insignificance. We exist for decades in a universe that will last for uncountable eons. Our civilization is thousands of years old in a cosmos billions of years old. The Earth will be habitable for perhaps another billion years. A tiny window in cosmic history. And yet there's something profound about being here now, in this epoch when stars still shine, when galaxies cluster together, when the cosmic microwave background can still be observed, when life can exist and consciousness can contemplate the universe. We exist at a moment of remarkable richness and possibility, after structure has formed but before it's all dispersed into darkness. Which brings us gently to the question of whether the universe's expansion might affect life's long-term prospects, and whether cosmic acceleration poses challenges for the far future survival of civilization. The accelerating expansion of the universe has interesting implications for the search for extraterrestrial intelligence and the possibility of life elsewhere in the cosmos. While dark energy doesn't directly affect conditions on planets or in solar systems, it shapes the observable universe in ways that might influence how advanced civilizations develop and whether they can communicate across cosmic distances. Consider first the question of whether dark energy affects the prevalence of life. The answer appears to be both yes and no. On one hand, dark energy became dominant billions of years after the first stars and planets formed. Life on Earth emerged about 4 billion years ago, long before dark energy's influence became significant. The conditions allowing planets, chemistry, and biology to develop were established during the matter-dominated era. On the other hand, dark energy's strength determines how long the universe remains hospitable to structure formation. If dark energy were significantly stronger, it might have prevented galaxies from forming at all. If it were much weaker, the universe might have recollapsed before life could emerge. The specific value we observe allowed sufficient time for complexity to develop, suggesting that dark energy's strength might influence whether universes can host life. This connects to the anthropic reasoning mentioned earlier. Perhaps we observe the particular dark energy density we do because only universes with similar values can produce observers. In the landscape of possible universes with different dark energy values, only a narrow range allows structure formation and the emergence of life. We necessarily find ourselves in one of these rare life-permitting universes. For the search for intelligent life, dark energy creates an interesting temporal constraint. Advanced civilizations can only communicate across cosmic distances if they exist simultaneously in cosmic time. Light-speed communication means signals take millions or billions of years to cross intergalactic distances. If civilizations rise and fall on shorter timescales, they might never contact each other even if both exist. Dark energy exacerbates this problem by redshifting signals from distant sources. A radio signal sent from a distant galaxy arrives, weakened and frequency shifted by cosmic expansion. The farther the source, the greater the redshift and the weaker the signal. For sources beyond our event horizon, signals can never arrive at all, making communication impossible regardless of how long we wait or how powerful the transmission. This means the pool of potentially contactable civilizations is limited not just by how common life is, but by the geography of cosmic expansion. Only civilizations in galaxies currently within a certain distance can potentially communicate with us. As the universe ages and the event horizon shrinks, this pool diminishes. Civilizations that might have contacted us if they'd existed earlier might be forever beyond contact if they emerge later. Some scientists have speculated about whether advanced civilizations might find ways to counter dark energy's effects. Could sufficiently advanced technology manipulate space-time to prevent expansion? Could wormholes or other exotic phenomena allow communication across expanding space? Current physics suggests probably not, but we're speculating about capabilities far beyond anything we can currently envision. A more practical concern for future civilizations is energy availability. The accelerating expansion means that in the far future, isolated galaxy clusters will have access only to the matter and energy within their bound region. No new matter or energy can be obtained from other regions. This creates fundamental limits on how long and how much any civilization can grow. Freeman Dyson, the theoretical physicist, explored these questions in a classic paper about life's long-term prospects in an expanding universe. He argued that intelligent life might survive indefinitely by becoming increasingly efficient at using energy, processing information more slowly as the universe cools, essentially hibernating through longer and longer periods to match the decreasing availability of energy. But Dyson's analysis assumed a universe that expands forever while cooling to absolute zero but never accelerating. Dark energy changes the calculation because the acceleration eventually creates a de Sitter space, a universe with a maximum possible entropy and temperature. This might prevent the slow, eternal survival Dyson envisioned, setting a hard limit on how long complex processes can continue. These considerations are necessarily speculative. We're thinking about timescales of trillions of years or more, far beyond anything we can test experimentally or observe. The physics of such extreme conditions might involve phenomena we haven't discovered. New theories of quantum gravity might reveal possibilities we can't currently imagine. Still, it's worth contemplating what cosmic acceleration means for the broadest possible perspective on life's place in the universe. If we're the only conscious observers in our galaxy cluster, then in the far future, our descendants or successors might be the only conscious beings in the observable universe, isolated in an island of matter surrounded by empty space. This isolation could be profound. No communication with other civilizations, no possibility of learning from alien perspectives, no chance of cosmic cooperation or conflict, just an island of awareness in infinite darkness, contemplating the history of a universe it can no longer fully observe. Alternatively, if intelligence is common, many such islands might exist, each unaware of the others, each developing its own understanding of the cosmos, each facing the same ultimate heat death. The universe would be filled with consciousness, but with consciousnesses that can never meet or communicate, forever separated by the expansion of space. There's something both melancholy and beautiful about this picture. Melancholy because it suggests ultimate isolation, the impossibility of contact with cosmic neighbours. Beautiful because it emphasises the preciousness of any consciousness that exists. Each island of awareness a rare and temporary phenomenon in an otherwise unconscious universe. These thoughts naturally lead us to consider what the discovery of cosmic acceleration means for our understanding of science itself, and what it teaches us about the process of scientific discovery. The discovery of cosmic acceleration offers valuable lessons about how science progresses, how theories are tested and revised, and how observation can overturn even deeply held assumptions. Reflecting on this discovery helps us understand not just cosmology, but the nature of scientific inquiry itself. Perhaps the first lesson is the importance of actually making measurements, rather than assuming we know the answer. Before the supernova observations, most cosmologists expected to measure how fast the universe's expansion was decelerating. The question seemed to be only whether there was enough matter to eventually halt the expansion, or whether it would continue forever while slowing down. The possibility of acceleration wasn't seriously considered by most researchers. This assumption wasn't unreasonable. General relativity seemed to predict deceleration. Observations of matter density suggested deceleration. The theoretical framework appeared complete. But the supernova teams didn't assume, they measured, and the measurements revealed something unexpected. This demonstrates the crucial role of empirical observation in science. Nature answers our questions, not our preconceptions. The discovery also illustrates how science is cumulative, building on previous work while sometimes overturning it. Edwin Hubble discovered the expanding universe in the 1920s. For decades, astronomers refined measurements of the expansion rate. The supernova cosmology projects inherited these techniques and improved them, expecting to extend and refine the existing picture. Instead, they discovered something fundamentally new. Progress in science often comes from taking existing methods and applying them with greater precision. Another lesson concerns the importance of independent confirmation. When the Supernova Cosmology Project first announced evidence for acceleration in 1997, the result was met with skepticism. Extraordinary claims require extraordinary evidence. But when the High Z supernova search team independently confirmed the finding in 1998, using different telescopes and analysis methods, confidence increased dramatically. The agreement of competing groups using independent approaches is one of the strongest forms of scientific validation. The subsequent confirmation from cosmic microwave background observations and baryon acoustic oscillations further strengthened the case. Each new independent line of evidence made alternative explanations less plausible. This convergence of multiple probes is characteristic of how scientific confidence builds. Rarely does a single observation prove a conclusion beyond doubt. Rather, multiple observations from different angles collectively build an increasingly complete picture. The dark energy discovery also demonstrates how unexpected observations can open entirely new fields of research. Before 1998, dark energy was not a major research topic in physics or cosmology. Now it's one of the central mysteries driving observational cosmology, theoretical physics, and experimental particle physics. Thousands of researchers work on dark energy-related questions. Billions of dollars fund missions to study it. An unexpected observation created an entire research program that continues today. This pattern repeats throughout scientific history. X-rays, radioactivity, the cosmic microwave background, and gravitational waves were all unexpected discoveries that open new windows on nature. Often the most important advances come not from answering expected questions, but from discovering unexpected phenomena that require entirely new questions. The continuing mystery of dark energy's nature teaches humility. We've measured its effects with increasing precision for over 25 years. We've constrained its properties through multiple independent observations. We can predict how it will shape the universe's future. And yet we still don't know what it actually is. This reminds us that observation and understanding are different achievements. We can observe phenomena we don't understand and make predictions about them without truly grasping their fundamental nature. 19th century astronomers could predict planetary motions precisely using Newton's laws, without understanding that gravity arises from space-time curvature. Early 20th century physicists could use quantum mechanics to make accurate predictions without agreement on what the theory meant or how to interpret measurement. Similarly, we can describe dark energy's effects and predict its consequences without knowing its fundamental origin. This situation also highlights the distinction between phenomenological and fundamental theories. A phenomenological theory describes what happens without explaining why. Einstein's cosmological constant is essentially phenomenological. It describes dark energy's behavior but doesn't explain where it comes from or why it has the value we observe. A fundamental theory would derive dark energy from deeper principles, showing why it must exist and calculating its properties from first principles. Science often progresses from phenomenological to fundamental understanding. Kepler's laws described planetary motion phenomenologically, before Newton explained them through gravitational theory. Newton's gravity worked phenomenologically before Einstein showed it emerges from space-time geometry. Perhaps dark energy awaits a similar transition, from phenomenological description to fundamental understanding. The search for this understanding demonstrates how modern science works at the frontiers of knowledge. Theorists propose models and calculate their predictions. Observers design experiments to test these predictions. The interplay between theory and observation drives progress, each informing and constraining the other. When observations don't match predictions, both theorists and observers re-examine their work, checking for errors or overlooked effects. This process requires both creativity and rigour. Creativity to imagine new possibilities and develop novel theoretical frameworks. Rigour to test these possibilities against observation and eliminate ideas that don't work. The combination produces reliable knowledge about the natural world, knowledge that accumulates over time even as specific theories are revised or replaced. The dark energy story also illustrates how science is a social enterprise. Thousands of people contributed to the observations, analysis, and interpretation. Peer review ensured that claimed discoveries were scrutinized critically before acceptance. Conferences and publications allowed researchers to share ideas and build on each other's work. The process is collaborative and competitive simultaneously, with groups racing to make discoveries while also sharing methods and data. This social structure has strengths and weaknesses. Strengths include the collective wisdom that comes from many perspectives, and the error-catching that comes from critical scrutiny. Weaknesses include potential biases or blind spots that affect entire communities and the difficulty of challenging consensus views. The dark energy discovery overcame consensus expectations precisely because multiple independent groups made careful measurements that were hard to dismiss. Looking forward, the search for dark energy's nature continues to exemplify good scientific practice. Making precise measurements, testing predictions, maintaining healthy skepticism while remaining open to new ideas, and building understanding through accumulation of evidence. The eventual solution might come from unexpected directions. Just as the original discovery was unexpected, there's a kind of peace in accepting that science is an ongoing process rather than a collection of final answers, that each discovery opens new questions, and that mysteries like dark energy are opportunities for future insight rather than failures of current knowledge. And perhaps this is what matters most, the recognition that understanding nature is a journey, not a destination, and that the journey continues regardless of individual endpoints. The apparent fine-tuning of dark energy's value leads naturally to one of the most controversial ideas in modern cosmology, the Anthropic Principle and the possibility of multiple universes. These concepts attempt to explain why the universe has the particular properties we observe by invoking selection effects and the requirement that conditions must allow observers to exist. The weak Anthropic Principle makes a modest claim. We can only observe a universe compatible with our existence. This seems almost tautological. Of course we find ourselves in a universe where life is possible. We couldn't observe a universe where life is impossible. But this simple observation has profound implications when combined with the possibility of multiple universes. If many universes exist with different values of physical constants, including different dark energy densities, then most might be lifeless. In universes where dark energy is too strong, galaxies never form. In universes where it's too weak or negative, cosmic expansion reverses before stars can create heavy elements. Only a narrow range of dark energy values permits the formation of stars, planets, chemistry, and eventually life. In such a multiverse scenario, we necessarily find ourselves in one of the rare universes with appropriate conditions. Not because the conditions are physically special, but because only these conditions allow observers to exist. The apparent fine-tuning of dark energy is explained by selection bias. We observe life-permitting values because we couldn't exist in universes with other values. The strong Anthropic Principle goes further, suggesting that the universe must have properties allowing consciousness to emerge at some point in its history. This version is more controversial, seeming to grant consciousness a privileged role in cosmic evolution. Many physicists reject this strong version, while finding the weak version more acceptable. The multiverse idea that often accompanies anthropic reasoning comes from several sources in modern physics. Eternal inflation theory suggests that quantum fluctuations during cosmic inflation create an infinite number of bubble universes, each potentially with different physical constants. String theory's landscape of possible vacuum states provides a mechanism for these constants to vary between bubbles. If this picture is correct, our observable universe is just one bubble in an infinitely larger multiverse. The particular dark energy value we measure is random, selected from the range of possible values across the landscape. We observe the value we do through anthropic selection. It's one of the values compatible with our existence. Critics of this approach argue it's not science, but rather a giving up on scientific explanation. If we explain dark energy's value by saying it could have been anything, and we observe one value through selection bias, we've abandoned the search for fundamental reasons why this particular value exists. The multiverse becomes an untestable hypothesis that explains everything by explaining nothing. Defenders counter that anthropic reasoning makes testable predictions. If dark energy's value is random within a range, we should observe a value neither suspiciously close to zero nor implausibly large for life. The observed value should be typical of life-permitting values, not special in any way. Some calculations suggest our observed dark energy density is indeed roughly typical of the anthropic range, neither the minimum nor maximum value compatible with galaxies and stars. This leads to an interesting prediction. If anthropic reasoning is correct, we shouldn't expect to find any fundamental reason why dark energy has its particular value. No elegant theoretical explanation will emerge. The value is environmental, like Earth's distance from the Sun. depending on local conditions rather than fundamental laws. This prediction could eventually be tested if we develop a complete theory of quantum gravity and find it admits multiple solutions with different dark energy values. The multiverse idea also connects to long-standing questions in philosophy of science about explanation and prediction. Traditional scientific explanation involves deriving observed phenomena from fundamental principles. We explain planetary orbits from gravitational laws, explain chemical properties from atomic structure, explain biological evolution from natural selection. Anthropic reasoning seems to work differently, explaining observations through necessity given our existence rather than through underlying mechanisms. Some philosophers argue this represents a new kind of scientific explanation, appropriate when fundamental parameters can take different values in different regions or different universes. Others maintain it's not really explanation at all, but rather resignation to the absence of deeper understanding. The debate continues. Regardless of one's view on these interpretive questions, the multiverse hypothesis has stimulated interesting theoretical work. Understanding how inflation can create bubble universes, cataloguing the possible vacuum states in string theory, and calculating which universes in the landscape can support life, all represent serious scientific endeavours that have advanced our understanding of theoretical physics. Moreover, the multiverse idea makes a testable claim about what we should not find. We should not discover a fundamental theory that uniquely predicts dark energy's observed value from first principles. If such a theory emerges, the multiverse explanation would be unnecessary. The fact that no such theory currently exists doesn't prove the multiverse picture correct, but it leaves room for the possibility. There's also something philosophically interesting about contemplating existence as one universe among many. It shifts perspective from seeing our universe as the unique physical reality to seeing it as one member of a vast ensemble. This is similar to the Copernican revolution displacing Earth from the centre of the cosmos, or the discovery that our galaxy is one among billions. Each step makes humanity seem smaller and less central, while expanding our understanding of reality's scope. Whether or not the multiverse picture is ultimately correct, it represents a serious attempt to grapple with apparent fine-tuning in fundamental parameters. The alternative is accepting fine-tuning without explanation, or hoping that future theories will reveal why dark energy must have its observed value. Each option has philosophical and scientific implications worth considering. The question remains open. Future observations might find evidence for or against the multiverse. Theoretical progress might reveal why dark energy's value is unique rather than arbitrary, or we might find ourselves permanently unable to answer why the universe has the particular properties it does, accepting this as a fundamental limit on scientific knowledge. In the end, what we're left with is not an answer, but a feeling that we're asking profound questions about reality's deepest structure, questions that blur the boundaries between physics, philosophy, and metaphysics. Having explored the technical details, theoretical frameworks, and philosophical implications of cosmic acceleration, it's worth stepping back to contemplate what it means to be human in an accelerating universe. This discovery has changed our cosmic story, the narrative we tell about where we came from and where we're going. For most of human history, the universe seemed eternal and unchanging. The stars wheeled overhead in fixed patterns. Constellations looked the same to ancient Babylonians as to medieval Europeans as to modern observers. This permanence suggested the cosmos was fundamentally stable, perhaps even eternal in both past and future. The 20th century shattered this picture. Hubble's discovery of cosmic expansion revealed a universe with a beginning, a history, a direction of change. The Big Bang Theory provided a creation narrative grounded in physics rather than mythology. We learned we live in a universe that began hot and dense, and has been expanding and cooling for billions of years. For decades, the question seemed to be whether this expansion would continue forever or eventually reverse. Both possibilities fit naturally within Einstein's framework. A forever expanding universe meant infinite time ahead, an endless cosmic future. A recollapsing universe meant a finite lifetime, with all of cosmic history fitting between the Big Bang and a future Big Crunch. Perhaps what matters most is recognizing that we're participants in an ongoing story, contributors to humanity's gradual understanding of the universe. The scientists who discovered cosmic acceleration built on work by Hubble, Einstein, Friedman, and countless others. Future scientists will build on current work, hopefully solving mysteries we cannot yet crack. This continuity across generations, this collective project of understanding nature, might be one of humanity's most noble endeavours. We won't live to see the end of the story, but we can participate in its unfolding, adding our observations and insights to the accumulating body of knowledge. And so we come to understand slowly that living in an accelerating universe means living with both knowledge and mystery, understanding and wonder, answering some questions while discovering new ones to ask. There is something profoundly beautiful about confronting mysteries we cannot yet solve, about standing at the edge of human knowledge and looking outward into the unknown. Dark energy represents exactly this kind of frontier, a phenomenon we can measure and observe but cannot yet fundamentally explain. In this chapter, let's settle into contemplating the aesthetic and emotional aspects of scientific mystery. Throughout history, humans have responded to mystery in different ways. Ancient peoples created myths to explain phenomena they couldn't understand. Thunder as the anger of gods, disease as punishment, natural disasters as signs. These myths provided psychological comfort, imposing meaning and pattern on a chaotic world. They also, importantly, closed off further inquiry. If thunder is Zeus's anger, why investigate the physics of electrical discharge? The scientific approach to mystery works differently. Rather than inventing stories to explain the unknown, science says _quote, _5, _quote, _ and looks for ways to find out. This requires comfort with uncertainty, willingness to admit ignorance, and faith that continued observation and thought might eventually reveal answers. It's an approach that keeps mysteries open rather than closing them with premature explanation. Dark energy exemplifies this scientific approach. We could easily invent stories about what it is. A new field, a property of space, a sign of extra dimensions, even evidence of divine influence. Some of these stories might even be correct. But rather than committing to any single story prematurely, the scientific community maintains what the poet Keats called negative capability, the capacity to remain in uncertainties and doubts without irritable reaching after fact and reason. This doesn't mean scientists are passive or resigned. The experimental efforts described earlier, Roman Space Telescope, DESI, Euclid, represent active attempts to gather more information, to constrain possibilities, to move from uncertainty toward understanding. But there's recognition that this process takes time, that rushing to conclusions can be counterproductive. That sometimes the most honest answer is we don't know yet. There's an aesthetic dimension to this as well. Scientific mysteries at the frontier of knowledge possess a particular kind of beauty, different from the beauty of understood phenomena. The electron's quantum behavior is beautiful once you understand the wave function and probability amplitudes. Dark energy is beautiful precisely because we don't understand it, because it points towards something deeper waiting to be discovered. And perhaps this is what's most beautiful about dark energy and similar mysteries. They remind us that reality is bigger than our theories, deeper than our current understanding, more mysterious than our attempts to explain it. The universe doesn't owe us comprehensibility. The fact that we can understand anything at all is remarkable. That mysteries remain is not a failure, but an invitation to wonder, to contemplate, to continue the never-ending quest for deeper understanding. In that wondering, that contemplation, there is peace. Not the peace of complete understanding, but the peace of accepting our place as finite beings in an infinite universe, temporary consciousness in eternal cosmos. brief moments of awareness in the vast sweep of cosmic history. The more we understand about cosmic history, the more remarkable our current cosmic moment appears. We exist at a specific point in the universe's evolution, a window of time with unique characteristics that allow both complex structure and comprehensive observation. Let's contemplate what makes this epoch special and what it means for our understanding of our place in the cosmos. The universe is currently about 13.8 billion years old. This might seem like an arbitrary time, but it's actually a privileged moment in several ways. We live after the universe has evolved enough complexity to support life, but before dark energy has dispersed structures beyond observability. This window is surprisingly narrow in cosmic terms. In the first few 100 million years after the Big Bang, the universe was too young for life. No heavy elements existed yet, still locked inside the first generation of stars. No planets could form from hydrogen and helium alone. To live their entire lives, fuse light to live their entire lives, fuse light elements into heavier ones, and die in supernova explosions, scattering those elements into space before the building blocks of chemistry existed. The first planets had to form, develop atmospheres, and cool enough to support liquid water. These processes took billions of years. Life couldn't emerge until the universe was several billion years old at minimum. On the other end of the timeline, the universe won't remain observable in its current richness forever. As dark energy continues driving acceleration, distant galaxies will redshift beyond visibility. The cosmic microwave background will cool until it's undetectable. Within perhaps 100 billion years, our galaxy cluster will be isolated in an empty void, unable to see evidence of the Big Bang or measure cosmic expansion using distant galaxies. Astronomers in that far future will face an interesting predicament. They'll observe a seemingly static universe containing only their local galaxy cluster surrounded by darkness. Without access to the cosmic microwave background or distant galaxies, they won't be able to determine that the universe had a beginning or is expanding. They'll lack key evidence that we currently use to understand cosmic history. This raises an uncomfortable question. Might we be in a similar situation now? Perhaps there were observational windows available to earlier epochs that have already closed for us. Evidence about the universe's first moments or its ultimate fate might have been observable billions of years ago, but is no longer accessible. We might be missing pieces of the cosmic puzzle that were visible to hypothetical observers in different epochs. This perspective shifts how we think about consciousness and observation. Rather than passive observers of an indifferent cosmos, we become the universe's means of self-understanding. The atoms in our bodies were forged in ancient stars. The thoughts in our minds reflect patterns in the physical universe. When we study cosmology, it's the universe examining itself, using our consciousness as an instrument of cosmic self-reflection. The universe created conditions for structure to form: stars, planets, chemistry, life, consciousness. Through an almost unimaginably long and complex process, it arranged matter in patterns capable of thinking about expansion, acceleration, and dark energy. We are those patterns, temporary organizations of matter and energy capable of wonder and understanding. This realization can feel either empowering or overwhelming. Empowering because it grants cosmic significance to consciousness and thought. Overwhelming because it emphasizes how precious and fragile awareness is, how dependent on specific conditions that won't last forever. But perhaps the appropriate response is neither pride nor anxiety, but simply gratitude. We exist during a remarkable cosmic moment. We can see stars and galaxies and understand what they are. We can measure cosmic expansion and discover its acceleration. We can contemplate questions about dark energy and the universe's fate. These capabilities emerge from billions of years of cosmic evolution and might only be possible for a limited time in cosmic history. Making the most of this moment means continuing to observe, to question, to seek understanding. It means appreciating the beauty and mystery of the cosmos while we can observe it. It means recognizing our place in the long arc of cosmic history. Not the center, not the end point, but participants in an ongoing story that began before us and will continue after us. And so we find ourselves at this privileged moment, this cosmic window of awareness and observation, temporary but real, brief but meaningful in its own right. Science describes the universe, its structure, history, and evolution. But description alone doesn't address questions of meaning and value, of why the universe exists or whether human existence matters. These questions live at the boundary between science and philosophy, between objective observation and subjective experience. In contemplating dark energy and cosmic acceleration, we inevitably confront questions about meaning. The universe will end in heat death, with all structure dissipating into cold. Dark emptiness. Dark energy ensures this fate by driving eternal acceleration. Given this ultimate futility, does anything matter? If all our achievements will eventually be erased by entropy and expansion, what's the point of achievement, of effort, of consciousness itself? This is an old philosophical question, taking new form in light of modern cosmology. The existentialists confronted similar issues. If the universe is fundamentally absurd and meaningless, how should we live? Albert Camus famously compared human existence to Sisyphus, endlessly pushing a boulder up a hill only to watch it roll back down. Camus concluded we must imagine Sisyphus happy, finding meaning in the struggle itself rather than in permanent achievement. Cosmic acceleration presents a similar challenge on universal scale. Everything we build, everything we discover, everything we create will eventually be lost to heat death. Not just individual works, but all of human civilization, all life on Earth, all complex structure anywhere in the universe. The ultimate futility is total and guaranteed. One response is nihilism. Nothing matters, so why bother? If the universe doesn't care about human achievements, perhaps we shouldn't either. We could give up on meaning and purpose, accepting that existence is pointless and our actions ultimately insignificant. But this response seems psychologically unsustainable for most people. We care about things even when we know they're temporary. We love people who will die. We create art that will decay. We pursue knowledge that will be forgotten. Temporariness doesn't eliminate meaning in our daily lives, so why should cosmic temporariness eliminate cosmic meaning? Others find meaning in connection, to other people, to life, to the cosmos itself. We're made of atoms forged in ancient stars. We breathe oxygen produced by photosynthesis. We're sustained by complex webs of ecological relationships. We're part of an interconnected whole, and this connection provides meaning independent of ultimate cosmic fate. The search for meaning in a universe described by science is deeply personal. Different people reach different conclusions based on their experiences, values, and reflections. Science provides constraints on what's possible but doesn't dictate how we should respond emotionally or philosophically to what we discover. What dark energy teaches us is that the universe is both comprehensible and mysterious, both explainable and profound. We can measure its effects precisely while remaining ignorant of its fundamental nature. We can predict the universe's fate while being unable to prevent it. We can understand cosmic acceleration while contemplating what it means for consciousness, meaning, and value. This dual nature of cosmic understanding, empirical and existential, objective and subjective, is perhaps the most honest response to scientific discovery. We acknowledge what we know and what we don't know. We measure what we can measure and contemplate what we cannot. We find meaning not by ignoring scientific reality, but by engaging with it honestly and allowing it to inform but not determine our sense of purpose and significance. In the end, each person must answer questions of meaning individually. Science tells us the universe is expanding and accelerating toward heat death. What we make of that fact, how we respond emotionally and philosophically, how we choose to live in light of cosmic futility, these remain personal choices, informed by, but not determined by scientific understanding. And perhaps that's appropriate. The universe presents us with mystery and wonder, with beauty and ultimate dissolution. Our response to these realities reflects who we are as much as what the cosmos is. As we near the end of this long journey through cosmic acceleration, it seems right to settle into acceptance and peace. We've explored the measurements, the theories, the implications. We've confronted mysteries that remain unsolved and futures that seem either distant or inevitable. Now let's rest in what we've discovered and find peace with both knowledge and uncertainty. Acceptance begins with acknowledging what we know. The universe is expanding. This expansion is accelerating. Something called dark energy drives this acceleration, constituting about 68% of the total cosmic energy budget. These are facts confirmed by multiple independent observations, as well established as any scientific findings about the cosmos. We also know the expansion history, from the Big Bang through inflation, from radiation dominance to matter dominance, from deceleration to acceleration. We know approximately when dark energy became dominant and can predict roughly what will happen in the future. The large-scale trajectory of cosmic evolution is mapped out, even if details remain uncertain. These observations represent genuine achievements of human understanding. Barely a century ago, we didn't know galaxies existed beyond our own. We thought the universe might be eternal and static. Now we've measured cosmic expansion across billions of light years and billions of years of time. This represents extraordinary progress in a remarkably short period. Acceptance also means acknowledging what we don't know. We cannot explain dark energy's origin or calculate its value from fundamental principles. We don't know whether it's truly constant or evolves over time. We cannot predict what new observations might reveal about its nature. Mystery remains, profound and humbling. This combination of knowledge and ignorance is natural and appropriate. Science progresses by expanding the boundary between known and unknown, not by eliminating mystery entirely. Each answer raises new questions. Each discovery reveals new depths to explore. The process is endless, or at least continues far beyond any individual human lifetime. Finding peace with the situation means letting go of the need for complete understanding. We can appreciate what we know without anxious clinging to it. We can engage with what we don't know without fearful resistance. Knowledge and mystery both have their place. Both contribute to our understanding of reality. There's peace too in accepting the universe's ultimate fate. Heat death seems inevitable if dark energy remains constant. All structure will eventually dissolve. All complexity will give way to maximum entropy. This might seem depressing, but it's simply how thermodynamics works. Fighting against it or denying it doesn't change reality. Instead, we can accept that everything is temporary, that all structures, including the universe itself, have beginnings and endings. This doesn't diminish the value of what exists now. A beautiful sunset isn't less beautiful because it fades. A meaningful life isn't less meaningful because it ends. Temporary things can still matter, can still be real and valuable while they last. Accepting cosmic mortality might even enhance appreciation for cosmic life. We exist during a privileged epoch when stars shine and galaxies cluster, when complexity is possible and consciousness has emerged. This won't last forever, but it's real now. Perhaps the transience makes it more precious rather than less. There's also acceptance of our limited place in the cosmic story. We're not the centre of the universe or its purpose. We're one planet around one star in one galaxy among billions. Our entire civilization is a brief moment in cosmic time. Dark energy was shaping the universe's fate billions of years before Earth formed and will continue long after our sun has died. This might seem to diminish human significance, but it can also be liberating. We don't bear the weight of cosmic purpose or the responsibility of eternal meaning. We can simply be what we are, conscious beings briefly aware of the cosmos, participants in an unfolding story we didn't start and won't finish. Accepting this limited role doesn't mean giving up on meaning or purpose in our own lives. It means finding appropriate scope for human concerns. We can care about our lives, our communities, our species, even our planet and solar system. We can pursue knowledge and create beauty and seek understanding. These activities matter on human scales, even if they don't alter cosmic destiny. Peace also comes from recognizing the value of the journey over the destination. Science is an ongoing process, not a finished product. The joy lies in the discovery, the observation, the contemplation, the gradual accumulation of understanding. Dark energy provides material for this process, questions to investigate, mysteries to contemplate. The fact that we don't fully understand dark energy means there's work to do, discoveries to make, insights to gain. This is exciting rather than frustrating when we approach it with the right mindset. The mystery is an opportunity, not a failure. We get to participate in humanity's ongoing effort to understand the cosmos. Finding peace also involves gratitude. We're fortunate to live in an epoch when the universe can be observed and understood. We're fortunate to have the scientific tools and knowledge to measure cosmic acceleration. We're fortunate to be alive during a time when these discoveries are being made. None of this was guaranteed or inevitable. Gratitude extends to all who contributed to this understanding. The scientists who made the observations, the theorists who developed the frameworks, the engineers who built the instruments, the educators who preserved and transmitted knowledge across generations. We stand on the shoulders of countless others, benefiting from their curiosity and dedication. There's gratitude, too, for existence itself, for the universe having the particular properties that allow structure, complexity, chemistry, life, and consciousness. The values of physical constants could have been different. Dark energy could have been stronger or weaker. The universe could have been inhospitable to observers. But it wasn't. We exist, and we can contemplate our existence, and that itself seems worthy of appreciation. Acceptance and peace don't mean passivity or resignation. They mean engaging with reality as it is rather than as we wish it to be. We can actively pursue understanding while peacefully accepting current limitations. We can work toward future discoveries while finding contentment with present knowledge. We can hope to solve mysteries while accepting that some might remain unsolved in our lifetimes. This balanced perspective seems healthiest for engaging with both science and existence. We neither cling desperately to certainty nor resign ourselves to permanent ignorance. We neither ignore mysteries nor let them paralyze us with anxiety. We engage, question, explore and contemplate, all while maintaining equanimity about outcomes. In the specific case of dark energy, acceptance means recognizing it as part of physical reality without requiring it to conform to our preferences. The universe accelerates. Space has energy. These facts don't depend on our approval or understanding, they simply are. Accepting them as features of reality, however mysterious, allows us to work with them rather than against them, and so we come to peace. With knowledge and ignorance, with time and mortality, with mystery and understanding, with our small place in an enormous cosmos. This peace isn't the absence of curiosity or the end of questioning. It's the foundation from which we can engage with reality clearly, without distortion from anxiety or clinging. From this peaceful foundation, wonder. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. From this peaceful foundation, wonder and understanding both flourish naturally, like flowers in good soil. Well, we've travelled together for quite some time now, haven't we? 2.5 hours through the expanding universe. From the first surprising observations of distant supernovae to the deepest questions about meaning and purpose in an accelerating cosmos. I'm grateful you stayed for this entire journey through one of modern science's most profound mysteries. Let's think back over where we've been. We started with scientists expecting to measure how fast the universe's expansion was slowing down, only to discover it was speeding up instead. We explored how this impossible observation became confirmed through multiple independent measurements. Type 1, a supernovae, the cosmic microwave background, baryon acoustic oscillations. We delved into what dark energy might be, from Einstein's cosmological constant to more exotic possibilities involving extra dimensions or modified gravity. We contemplated the implications, how dark energy determines the universe's fate, how it creates cosmic horizons beyond which we can never see, how it isolates galaxy clusters into islands of matter separated by ever-increasing voids. We thought about what this means for life's long-term prospects, for the search for other intelligent beings, for humanity's place in the cosmic story. And we explored the deeper questions. Why does dark energy have the particular value we observe? Is it constant or evolving? Does it point toward a multiverse of universes with different properties? What does it mean to live in an accelerating universe, to exist during a privileged observational epoch, to be conscious beings contemplating our cosmic context? The answer, as honestly as I can give it, is that we don't fully know. Dark energy remains mysterious despite decades of precise observation. We can measure its effects, predict its consequences and constrain its properties. But we cannot yet explain what it fundamentally is or why it exists. This is both humbling and exciting. Humbling because it reminds us how much we still don't understand about the universe. Exciting because it means major discoveries likely await. Perhaps the answer will come from the next generation of observations, from Roman Space Telescope or DSI or Euclid, finding subtle variations in dark energy's behaviour that point towards specific theoretical explanations. Perhaps it will come from theoretical breakthroughs, new frameworks for understanding quantum gravity or space-time that explain dark energy's origin. Perhaps it will take forms we cannot currently imagine, requiring concepts and mathematics not yet developed. Or perhaps dark energy will remain mysterious, a phenomenon we can describe but not fundamentally explain, at least in our lifetimes. That would be okay too. Science is a long process extending across many generations. We contribute our observations and insights, and future scientists build on them. The complete understanding might come long after we're gone, but we participate in the journey regardless. If you've enjoyed this slow drift through cosmic acceleration and the mysteries of dark energy, I hope you'll subscribe to explore more questions at the boundaries of human knowledge. Your support through likes and subscriptions helps others find these peaceful ways to contemplate profound topics, and to those already subscribed, thank you for being part of this community of curious minds seeking understanding and wonder. I'd love to hear your thoughts in the comments. What aspects of dark energy fascinate you most? Do you find the universe's accelerating expansion inspiring or unsettling? How do you think about humanity's place in a cosmos dominated by phenomena we don't understand? Your perspectives and questions enrich these explorations for everyone. Wherever you are in the world right now, whether you're in a quiet bedroom watching the night sky, or a busy city where stars are hidden by light pollution, or somewhere in between, I hope this journey has brought some peace, some wonder, some sense of connection to the larger cosmos. I hope your breathing has slowed over these past hours, that your thoughts have quieted, that your body feels heavy and comfortable, ready for sleep. I hope you found some beauty in contemplating cosmic mysteries, some comfort in our shared human quest to understand reality. Look up at the stars if you can see them from where you are, or imagine them if you cannot. Each one is a sun, many with their own planets. Between those stars stretches space, expanding, accelerating, driven by dark energy we're only beginning to understand. Farther out are galaxies, billions of them, each containing billions of stars, all being carried apart by the same cosmic acceleration. And yet, despite the vast distances and incomprehensible scales, despite the mysteries we cannot solve and the futures we cannot prevent, here we are, conscious beings capable of measuring cosmic expansion, curious minds able to contemplate dark energy, temporary patterns of matter and energy aware of our own existence and questioning our cosmic context. All those galaxies receding into the darkness, all those stars destined to eventually fade, all that structure that will someday dissolve into maximum entropy. And yet, now, in this moment, it all exists, shining, spinning, evolving, creating conditions for complexity and consciousness and wonder. There's something profoundly peaceful about accepting both the grandeur and the impermanence of it all. The universe is vast and ancient and mysterious, and we're small and temporary and limited. But we're here now, able to observe and think and feel and contemplate. That seems like enough. More than enough, really. It seems like a gift. So rest now, if you can. Let the universe continue its expansion without you for a while. The acceleration will proceed whether or not you're watching. Dark energy will keep pushing space apart. Distant galaxies will keep receding. The cosmic story will continue unfolding. But you've done your part by wondering, by contemplating, by seeking to understand. You've participated in humanity's long effort to comprehend the cosmos. You've honoured the mystery while pursuing knowledge. You've found your own meaning in a universe that might not provide it from outside. Sleep well, knowing you're part of something vast and ancient and ongoing. Dream of distant galaxies if you wish, or of dark energy pervading space, or of the slow heat death that awaits all things. Or dream of nothing at all. Let your consciousness rest as the universe expands around you, gently, slowly, eternally. You're made of atoms forged in stars billions of years ago. You're sustained by a planet orbiting a typical star in a typical galaxy. You're a temporary organisation of matter capable of thought and feeling. You're the universe becoming aware of itself, if only briefly, if only locally. And that's beautiful, that's meaningful, that's enough. Good night, traveller through space and time. Good night, conscious pattern in the cosmic flow. Good night, fellow wanderer at the mystery of existence. May your rest be peaceful, and your dreams be filled with stars. Good night.